right, I think we're about ready. Right? Okay. Today I'm going to be talking about the rendering architecture that we did for our Walking Dead game. It's basically a top-down perspective map game where players build bases and sort of attack each other. Very popular genre on the asset store, on the app stores. So my name's Jason Booth. I've been in the game industry for about 25 years now. I actually started as a 3D artist, came out of music school. I was creative director for a while, and I spent a lot of time doing code. So I'm sort of all over the map in terms of my skill set. I've worked on a lot of games. The presentation that I'm doing today is also written by Greg Siegert, who's our graphics engineer, and he's got a ton of credits too. So if you're not familiar with me from any of those, then I also do Microsplat and Megasplat on the Asset Store. They're amazing terrain shaders, so check them out. So let's talk about the project goals. Basically, our designers wanted a really large world. It needed to be this big scrolling map. They wanted spaces for up to 50,000 players as a sort of high watermark. And so what they basically needed was 1024 by 512 game tiles for players to place bases and things like that. This would be a freely scrollable world. So the user can just swipe and move around it. And it's based on the Virginia, D.C. area, which is where the comic takes place. And so you can see in this map, you can kind of see the size of a view on here, pulled back, like how big your phone is. So we have a small team to build this. Now, what you consider a small team is highly variable, but for me, 2 artists is a small team. So we had 2 artists that were almost full-time on the map. And we need this to work on really low-end hardware. By low-end hardware, I mean OpenGLS 2.0 with 1 gig of RAM. So these devices still count for about 40% of the Android devices on the market. And so we need to target those devices. So we have to run on those as our minimum spec. And because we're a mobile game, one of the things is that they limit the size of the game to about 100 megs on the asset stores, app stores. And so we need to stay under that, which means we need to stream a lot of this data to the user. And we build this all in Unity 5.3. So if we were not constrained by these particular constraints, we would probably use very different techniques. If we had modern devices, we could use instancing and things like that, and there's a lot more available. So a lot of your result is driven by the constraints you work under, and you choose your techniques accordingly. So here's some screenshots from the game. It's a very detailed world. Again, it's the DC area, so it's these cityscapes. There's lots of, litter and vehicles and things like that because it's post-apocalyptic. We do full day-night cycles. We do weather. You can see little guys walking around on the map here. Those are little zombies you can destroy. We kind of sort of create little stories in the scenes as well. Here's more of a distant view when you're pulled back, and so you still have all that street stuff here pulled back, and then you have sort of landmark places like the White House, places from the comic that are sort of known locations, and places from the real world that are known locations that we have to model as well. And then when you really pull out, you see kind of how big or how much detail is in one of these shots, right? There's an incredible number of objects that we're drawing, and we have to get this all working on our low-end devices. So let's talk about first how we created all this stuff. We use a mix of procedural techniques and hand-placed content. We need to hand-place things like the White House, these sort of key landmarks from the real world or the show. And then we used hand placement to solve things that are hard to solve or harder to solve procedurally, like managing where roadways and overpasses go and bridges over water and certain water edge features that were just easier to make one of our artists spend 2 or 3 days doing that than it was to solve those problems. And then there's certain story elements we had to place as well. And then for the procedural, we really want to use a procedural to sort of fill out all the rest of the stuff. And so we allowed the artists at a very high level to paint what type of areas they wanted where, so they could say like, oh, I want city over here, and I want suburbs over here, and give them a high level way to do that, and then we procedurally generate the details down there from the data they provided. I'm a big fan of procedural stuff, but I'm also a big believer that you have to keep the artist's control, otherwise it just gets in the way. And so we wanted, even in these procedural systems, to generate little bits of story, these dead inside signs and things like that, little stories about what happened sort of after the apocalypse. And we actually wanted to put all the action in the map. So we actually have zombies moving around on the map and walkers and different little survivors running around and attacking each other and stuff like that. So the first thing we did is break up the world into 32 by 64 regions. Now, these aren't gameplay regions. These are just used for loading and rendering. And at any given time, we'll have about 4 to 6 of these rendering and more of them loaded. And we paint down which region goes where in sort of a 2D tile map editor that I whipped up really quick for the artists. And so they can basically say like what region goes in each spot and sort of tweak it. And they ended up using this to solve sort of road pathing problems and things like that as well, because it gave them a very high level way to sort of construct the world. And then all of that stuff gets turned into the final map. For hand placing stuff, we have kind of a world editor, and this is just a special scene in Unity that gets loaded, and they can move around this scene, and at any point they can instantiate the procedural data for the world and place hand-placed objects. And so these red boxes you see are clearing radiuses. So they will clear out whatever the artist says to clear out. They can clear out everything, or they can say like, no, leave the roads because I want the road systems. And they can actually attach these to the objects as well, so that when they place objects, it just clears out the procedural underneath of it. And then they sort of instantiate a view at a time while they work on it, because if you actually tried to instantiate the whole map, even on a high-end PC, it's going to run out of memory. And so then all this data about the hand-placed stuff and the which procedural systems to use where gets compiled down in a compile step. And so we basically go over each of these 32 by 64 blocks, and we generate the procedural data, and we Boolean that with the hand data, basically clearing out stuff so that it makes room for it, following a rule set. And then we clear things like, hey, don't have things in the water that shouldn't be in the water, stuff like that. And while we're doing this, we generate a bunch of information for AI path planning, stuff like that, and we save this into what we call a prefab stream. And the prefab stream is what actually gets sent to the user via an asset bundle. While we're doing this, we also compile down a bunch of terrain data about how to render the actual terrain. And we compile a bunch of info for the server so that the server can know, like, hey, where are all the police stations? I want to spawn things there. Or where are grocery stores? Because that's where food should be. So the prefab stream is sort of our own version of a nested prefab. Basically, it has 2 uses. One is at runtime, and one is for design time. At runtime, really what it is it's a game object reference with a list of transform locations. Basically, where do you want to put this prefab? And what we actually do is we pack that transform down because our block size is known. We know that we're in a 160-meter area. So we can pack that into 7 shorts, basically 3 for position, 3 for rotation, and 1 for scale, because we only do uniform scale. And that saves us a lot of data. And then we can unpack that when we need it. And so what this does is if I save this as a scene, it's about 3.6 megs. If I save it as a prefab, it's about 2 megs. And if I save it as a prefab stream, it's only 41K. So basically, by building our own file formats, we're able to really cram down the size of things to allow us to stream this data to users, taking advantage of what we know about our own sort of data. So there's another use of prefab streams, which is at edit time. And so at edit time, there's a bunch of extra code in them that allows them to do things like randomization, stuff like that. So when it goes to generate one of these areas, it can randomize all these elements and create, little subtle variations on everything. And so everything's built up from these small little components. So you have like a house here, but it can actually swap out what its roof structure is, which may swap out what type of awnings are on it, and create all these little variations. And because it's a hierarchical nested prefab system, we can basically then randomize up and down a chain of objects to get lots of variation, where effectively what we end up doing is having this hierarchy of like, hey, in this plot here, well, we might decide it's a park in one case, or it might be, a parking lot in another, and then the parking lot will generate all of its data about what it's going to look like in that particular instance. So we get a ton of variation, and we get a nice workflow sort of up and down the chain. And in the editor, they can unpack and randomize these things and just sort of test them very easily. So when we're compiling these things, we actually break the prefab stream into 3 lists. So if the object is put on a layer that's low, medium, or high, we'll break it into the right list, and then we can basically decide to not draw those objects on really low-end devices. Now, we hardly ever use low because it's really aggressive, so that's kind of our like super fail-safe. We tend to have most devices on high or medium. And then when this is actually compiled down, it's all flattened. There's no hierarchy or anything when it's actually delivered to the user. It's sort of the final result in these 3 streams of detail levels. So to render this, what we actually do is compute the visible bounds from the blocks, which have a bounding box, and then the view frustum, and we figure out which ones we need to render. And we expand that region, and we kick off loads for the regions around it. And we do this in sort of a spiral pattern, so the ones that you're looking at will load first. And then these basically get unpacked on another thread because they come in this pack transform format. We need to convert those into a matrix. And so we go off on another thread, we unpack all the data, and when it's done, we can then submit it for rendering. And in this, because this code is really, it has to be fast because in WebGL we don't have threads, so we have to do it on the main thread. Luckily in WebGL we usually have a decent machine compared to a low-end phone, so it's not really a big deal. But we don't use any mathf or vector functions because those math libraries are incredibly slow. And so then once they're unpacked, we can submit them for rendering to the render engine. But we run into a problem here, which is that we're on OpenGL 2.0. We don't have instancing or any of the sort of modern features, and we're not even in that version of Unity. But even if we were in a newer version of Unity that had instancing and stuff like that, we can't use it because we're on OpenGL 2.0 and it doesn't support those features. And so this is going to be thousands of draw calls, and we need to figure out a way around that. Now, there's another option, which is static combine of all this stuff into meshes or even doing this dynamically. And it's not really feasible. If you static combine it, it's going to end up gigs of mesh data that you need to download. And if you try to do it dynamically, that's just going to be way too expensive. So what we did was abuse the dynamic batching system in Unity. And what dynamic batching does is it takes all little tiny objects and tries to combine them and draw them. And it turns out that it can do this really fast. And the trick is you have to stay under 900 attributes. So an attribute is a piece of data about your vertices. So if you have UVs, positions, normal, and tangents, and you have 4 attributes. So you divide that number by 4, and that's how many vertices you can render. Now, on some APIs, like on DX11, it's a little different than DX9 in terms of the total number because they have another attribute there. But generally, it works out to about 180 vertices per object. So as long as we build our entire world out of stuff that's super low poly and all on the same texture sheet and material, then it'll all get combined and drawn as one thing, which is pretty cool, but it's quite a lot of restrictions to put on the artists. So then we just instantiate all these things, right, and draw them. Well, we can't really do that. The traditional approach to this says, hey, use pooling, right? But most pooling systems, they do things like, mess with the transform hierarchy or enable and disable objects when they're not in use, which is really heavy when you have this many objects. And besides, it's going to be too much memory because if we're pooling all this stuff, at some point, we're going to be looking at the country and we're going to have all the city stuff loaded, right? So we can't really afford to have this all, and there's not a great way to load it in and out because then suddenly you're not pooling it anymore. So we did make a thing called the hide pool. And basically the idea here was let's just do everything in world space and we'll just move objects to where you can't see them when they're not in use. And we don't do any component activation or deactivation, and we have our own version of the update loop for things that need polling that can register and unregister with it. But this is still way too heavy because we don't solve the memory issues with this, and now we have a scene with just tons of objects in it, right? So we can't really use this. But we still do use it for some things. We use it for the 3D characters, and we use it for icons and bases, which are heavily reused and are used all over the map. So next I tried using graphics draw mesh. Let's just submit the stuff. We already have it in what looks like a draw list anyway, so we'll just submit it. So we unpack those transforms into this list of matrices, and then we just submit each one to the render engine. The problem with this is that it's still slow because you have to submit it every frame. And at first I thought, hey, can I just get, hey Unity, can I just get a graphics draw mesh with a matrix, list? And then, hey, I can just submit them all at once because maybe that's where the overhead is coming from. And they were kind of like, hey, yeah, you could put that into the engine because we're a source license. And so I tried that. And it turns out that's not actually where the issue comes from. Basically, the issue comes from the way internally these lists of actual things are rendered and managed. Just dealing with that management every frame was very costly. And I also explored using command buffers, but the problem with command buffers is they don't go through dynamic batching, so that was a dead end right away. Because the idea of the command buffer is like, hey, now I have this list, and I just submit this one list and say render it. But because it doesn't go through the dynamic batching system, that was out. So finally, I decided I'll just add my own API to the engine. And I really don't, we have access to source, but I really don't try to use it because I don't want to now own a million lines of code that's not mine, right? If I start changing things much, it becomes hard to merge, it becomes hard to manage. It's really not something I want to do. But if it's targeted and a very simple change, then I'll consider it. And we added what we call graphics draw mesh persistent. And the basic idea here is that those render lists that hold all the nodes that are actually going to get rendered in your frame now have an ID associated with them. And when the renderer comes along to clear out that list, it says, hey, if you have an ID that's not 0, then I don't clear you. And so now we can submit all of these renders to the frame once, and they'll stay until we tell them to actually go away. And while we were there, we raised the dynamic batching limit because it was really hard to keep things under the right number of vertex counts. So we kind of played with those numbers a little bit and got a little bit better batching out of it. And yeah, it ended up being about 30 lines of C, so it's not really a massive change, and that's something we could live with doing. So the result of this is that we start out with 6,800 meshes here. That's about almost 1 million vertices. And then we end up drawing this in 217 draw calls because it all gets combined via the dynamic batching, and we save 6,600 draw calls. So that's pretty good. So characters and animation, pathfinding, and AI. So we know we have to batch this stuff somehow because draw calls are our enemy on these low-end devices. But our characters, they're not really seen up close. They're these little guys you see moving around. They're very small. They don't need a huge animation set. Normally I would think, like, let's just put it all into a texture and sample in the vertex shader and do all our animation in the shader. But OpenGL doesn't support sampling in the vertex shader, and even in OpenGL 3.0, when the devices don't have unified memory, it can be very slow to do that. So we need another solution. What we decided to do is just to make mesh flipbooks. So at load, we basically take the animation and bake out all the frames as unique meshes. And so then we can just swap the mesh on the thing to make it animate, right? And this means we don't really get blending and stuff, but for our uses, that's fine. There are ways you could get that. You could pre-generate all the blends or something, but we didn't really need that. And so the only real downside to this is that it takes a lot of memory. And so on high-end devices, it takes about 40 megs. On low-end devices, we generate less variations, and then it takes about 10 megs of data. So we need to move these guys around this world, and this world is really detailed and complex. So we need some kind of navigation system, and we're not going to use navmesh for this. It's going to be way too slow. So what we actually do is raycast in the map compiler. We raycast down and up to figure out where, basically, is there open space in the range that the things are allowed to walk on the ground floor there. And that handles overpasses and things so they can walk under the overpasses. And this data is stupidly low res for a reason I will talk about later. And basically, it ends up 64 by 64 bits of data, right? So it's packed really tightly. It's just, can I walk here or not? And for the entire world, it works out to be about 1 mega data. And so it's only like 2K of data loaded at any given time that we're really dealing with. So while we do this, we have to figure out where the player can put bases on the map that they can attack each other with and stuff. And so we had to figure out where they go, because we want these little bases graphics to actually slot into the map. So we have to figure out where the open cells are that we can afford to put these things and what size we have to work with. So we basically scan through that navigation data, and we find the largest open spot in each of the, we break the thing into 16 by 16 places, and then we break each of those into 4 by 4 and figure out the largest size we have in there. And then we just pack that down into a byte So now we have a byte that stores the information about that. And so that works out to be 65K for the entire world, which is a huge world. And now we know basically, hey, here are all the places we can put bases and what size they can be. And then if a base is there, we just mark a bit in that mask. So the camera will intersect with large objects if we don't do anything. And we want it to have this nice smooth arc as it goes over things when you're really zoomed in close. So we need some kind of avoidance data. So what we did for this is we basically take that 16 by 16 grid again, and we figure out all the heights of things in those grid cells. And then what we do is pack that down. We choose the 4 best heights that work for us, which is basically the top height, the lowest height that's significant above a certain height, and then the 2 heights that are most used in between. And those become our 4 heights. And so then we basically use 2 bits of information to say which of the 4 heights it each is. So this ends up being 16 kilobytes for the entire world because it's packed so small. But from that, we can build a CatMul-ROM spline for the camera and interpolate that to get a nice smooth motion. And we also use it for path planning for flying stuff. So the simplest AI is the wandering walkers. They basically just wander around as cannon fodder. The user can click on them and they'll blow up, or they can, the survivors will shoot them with their guns. And so all they do is they raycast in a random direction, and they turn, and then they shamble that way, and then they do that again. Very, very simple. But they're raycasting through this bit field, and they don't have to raycast very far, so it's very fast even for hundreds of these guys. And so we have a lot of ambient life too, like birds, flocks, and things like that. And what we do for their behavior is we basically teleport a control point around the area, and then they all flock to the control point. And when they're flocking, they actually raycast out and look at the height field data to figure out whether they need to fly up over a building or around it, and do sort of a typical steering behavior around the map. And we'll do this with hundreds of birds every frame. And again, because that whole data structure is like 0.008K, right? It's really, really small. That will fit in the cache on any mobile CPU. And in some cases, it'll fit like right in the registers. So there's no memory cost in looking up this data. It's super, super fast to work with. So one of the things is if you can really make your data small, then it's going to go a lot faster because memory bandwidth is the biggest thing to avoid on CPUs. So we can do that for hundreds of birds every frame. And then the artist actually places landing spots in the prefab streams. They're like, oh, I have here's a chimney, so I'll put a landing spot on there, and then anywhere there's a chimney, the birds can land. And what actually happens is every frame, one of these landing points will wake up, and it'll tell a random bird, like, hey, come land here. And then that bird will start seeking to that spot instead of the main controller that it's seeking to. And when it gets close, it'll just like linearly fly in. And so you can see how these birds are just like landing and flying away. And that creates like really realistic behavior, which is really nice, but super cheap. And again, that's packed down into really, it ends up being 3 shorts for the position, so it's super small. So for the guys running around on the map, we have these little squadrons that run around as like a little team. And so there's a blue line there. That's actually the A-star pathing that we do through the level. So we do a traditional A-star when they get to a new block because they can run across the entire map. And so when they cross into a block, they'll do an A-star to get through the next bit that they need to get through. And the controller will move linearly along the A-star, and then they all flock to follow it so that it smooths out the motion. And you can see these little red and blue lines coming out of them. Those are actually the raycasts that they're doing to do local avoidance. So you'll see this one guy kind of crosses over because he detects that the car is there and moves around it. So even though we're doing that a lot, it's still pretty cheap because, again, the data that we're looking up in is just a bunch of bits that we're sampling, and so it's very, very fast. And we even stuck in things like they turn into a boat when they cross water, and so we have guys in the player bases, and this is obviously way closer than you'll ever really see them. But they will sit and they'll shoot walkers when they're not busy fighting other players. And so as these walkers wander around, they basically when they cross one of those block boundaries, the 16 by 16 subdivision block boundaries, they'll update themselves as being in a different cell of that, and then the survivors can just look at the neighboring cells in the spatial hash and very quickly look up and find if there's walkers to shoot and shoot them. We have a feature called walker swarms that is basically simulating the herds that you see in the show, in the comic, where hundreds of walkers are sort of swarming together. And we treat this kind of like a particle system. So essentially they spawn and they start walking towards a control point, and then they blow up when they get close. And so if there's a player around, it'll use the player for the control point, and they'll start swarming towards them. And when you put this all together on an actual game, you can see these like massive herds of walkers moving across the map and attacking players, which looks really cool. And the only way we can really do this is to really, make sure that this stuff is super cheap to do so that we can have a lot of it. So some general optimizations on this. I don't know who said this, but I just remember it, which is for every order of magnitude in call counts, take 10 years off your coding style. Basically, if you're going to write really fast, tight update loops, you don't want to have, you don't want to use update, first of all, and you don't want to use virtual functions and sort of object-oriented kind of stuff. In fact, you want to like inline a lot of functions and really strip it down. And really treat everything like you're writing a particle system. And a particle system, you have an array of particles, and you zip through the array, and you update everything at once. And that's generally how you should code things if you're going to have thousands of them. Unity specific, don't use their math libraries. They're unbelievably slow. They do really inefficient things. They call into C++. They convert to doubles. They do all kinds of things they just should never do. And they should basically burn in the fires of hell. So the basic thing with this is just be kind to the cache, right? There's a lot of stuff on data-oriented design and all these things, but really what it comes down to is that what CPUs do really well is zip through memory in a linear order and process things. And so you really just need a big block of things that are all nicely arranged, and you just basically run the same routine on them all. This is much like what shaders do, right? They take a block of pixels and they process them. And if you design your data that way and you keep the amount of data that you need to work with really small, then it'll all fit in the cache, and suddenly the CPU will go way faster than you ever thought it could. So that's why we pack all these things down to as small as we can get them. And because we're working on Android, we don't really know the size of these things because there's a billion devices. So we have to just cram things down as small as possible. So don't jump straight into threads. This is a common thing I see people do. They're like, hey, this code is so low, let's thread it. But the problem is their code is slow. So if you thread it, now you just have 8 processors writing really code, using code that's slow. And if you didn't get your data structure small, now you're copying tons of data to each of these processors so they can all run slow. So fix your code first, and then really look at that data size and see if you can get it organized better and smaller. And then you can look at amortization, because now you're asynchronous. And guess what? If you've done all these things, then actually moving to threads is really easy because you've done all the parts, right? You've made it asynchronous. You can now start the job and wait for it to return when it's done. And you've optimized things down into a cache-efficient manner that can easily be copied to another thread. You're ready to thread. And a lot of times you'll find you don't really need to thread at that point because your stuff runs really fast. So let's talk about train and water. The train has to be ridiculously efficient because we have all this stuff on top of it. It can't use a lot of memory because we're using it for other stuff, and it's got to look decent enough. So the first trick we did here, this is something Greg thought of, and I thought it was really smart, is take advantage of a different color space. So if you look at JPEG compression, what they actually do is they have a luminance value, which is really high res, and then the chroma values are actually kind of mashed to hell, and they get a lot of compression out of that. And that color space, it works really well. So we'll do the same thing, but what we'll do is we'll pack 4 luminance textures into one texture. So now we have like 4 terrain types. They're not really terrain types because if I take any of these and I color it different colors, it kind of looks like a different thing anyway. So I can kind of get more terrains out of each one of them than just one, right? Because if I take it at the view distance we're at and the sort of the scale, if I take it and I make it brown, it's going to look like dirt. If I make it green, it's going to look like grass. They're sort of noise signatures. And then we can do a traditional splat map thing, and we'll do this at vertex resolution. We'll store the weights in a splat map, so you have an RGBA mask that stores the weights of 4 things. And then we can use the luminance data as if it's a height map to do height map blending on it, which gives us nice transitions. And so if you just look at the luminance, you get this nice transition between these 2 textures here. And it looks like very high-res data, which is great. Our chroma actually looks really low-res. It doesn't really look like much at all. It's all blurry. It's just at the vertex resolution. But when you apply that chroma to that luminance, you end up with this, which looks really nice, right? Because you have that height map filtering to determine which chroma value you're taking, and you have these different noise signatures, and you actually get something that looks like a real terrain. So what we do is we store those chroma values. So we store a chroma value for each of the 4 luminosity textures, and we store those in the vertices in UV1 and 2, because they're 2 components each instead of 3 like in RGB. And then our splat weights are stored in the colors. And so now what we basically do is we can sample our texture and do our resolve. Well, one of the problems that we ran into right away is how to author this, right? So I have a free vertex painter. It's free on my GitHub. It's extensible. It has an extensible brush system. And so what I did was write brushes for this that let us declare, like, these chroma values with this lumen texture, equals this terrain type. And then you could just paint on the terrain using the vertex painter right in the editor, right in the world. And then we take that data that's on the vertices, we read it all back, we convert it to RGB, and we palletize it to shrink it down. Because the chroma values are, one, not that important, and there's not that many of them, so it palletizes well even when we convert it back to RGB. And then at load time, we can unpalletize that data and convert it back to the CBCR. And then we can just put it on our UVs again, right, to render it. So what this means is that we have one texture that we sample, which is a 1024 texture for the luminance data, and we have about 3 megs of data for the entire world for all the splat mapping. So water. Again, we need it to be pretty cheap, same sort of things. So we render the underwater part of the terrain as part of the terrain shader. So basically, the terrain knows the height of the water, so it just fogs itself and does its own shorelines. And then we take the water mesh. Now, normally to do good water, you need a depth map, and we don't want to render a depth map because that's really expensive. So the water mesh is just the terrain mesh. It's the exact same positions. And then we know what height the water's got to be at, so the difference between where my vertex is and where the water height is my depth. So we move it, we just set it back to the water height, and it pops up, and now we have a depth, right? So we can use that depth to do all the depth map type stuff, like fading based on distance and transparency, et cetera. And we don't have to render a depth map, which is a huge cost and a huge amount of texture data. And then we sort of do the traditional sort of water stuff, sine waves and stuff to make it wave around. And so what we're left with is we have a 1 texture sample, 1 draw call, 1 sample terrain, and we have the same thing for our water. So it's incredibly cheap. And then in motion, you get a little water motion. It's not Uncharted, right? But for a low-end mobile game, it's pretty good. So lighting. So we did something we call spherical lighting approximation. And so the basic idea here is that rendering full PBR was too expensive. There's a lot of calculations. And we wanted PBR because it looks great. And so what we did instead was we render a sphere. And we render the result of the PBR lighting from any number of lights to these spheres as both a diffuse response texture and a specular texture. And then we do this for subsequent MIP levels. We change the smoothness. And so now by changing the MIP bias, we can get different smoothness amounts on our specular and get really shiny to not shiny. And we can do log space encoding on this so we get HDR for free. And then at runtime, rather than actually doing any lighting calculations, we can just choose a MIP level and look up into the texture, and we're done. So the advantage of this is that we can have any number of lights, right? So because we only have to light this one object with Unity's lighting system. And we render that sphere, and we're done. And it doesn't matter if we have 8 lights or 2 or a skybox or whatever. We have to do some little tricks to make it work with shadows, basically subtracting out the primary light. But it works out to be about 20-25% faster than Unity's lighting solution for our stuff. It has some disadvantages. We don't support anything but infinite directional lights because we can't have local point lights because everything's using the same lighting data, effectively. Everything's lit from this one sphere and just looking up its angle into that sphere, basically. And there is some stuff with the specular response that's a little different, but for us it actually made things a little more stable. And when we want to do reflective stuff, we had to do some approximations there. But generally it works pretty well. So for shadows, we needed shadows because it makes the game look moody, and it's a zombie game, right? So it needs to look moody. And the traditional techniques are way too costly. We wanted something that we could pre-render. We weren't sure if we needed that. In the end, we do actually render the shadows every frame. It turned out to be fast enough. And there's this old school technique that we sort of thought of, which is just like taking the objects and flattening them and smearing them across the terrain, but it has a lot of problems, and so that really wasn't a solution for us. So instead what we do is we render a top-down view of the world. And we basically get a depth buffer from that. So now we know how far from the ground everything is. And then we can blur that in various ways to create our shadows. So if we blur it in the angle of the light, we can then sample that texture and tell whether we're in shadow and actually how far we are from the thing casting the shadow, because if it's really high, we know we're really far, and so then we can soften the shadow, et cetera. And we also do a blur based on how close we are to the bottom of the object, and we can use that for ambient occlusion. So what you end up with is with shadows off, you have this. You add the shadows in, and now you get these nice soft shadows coming off the objects. And then you get your AO in there. And you get this all actually in the object shader as the shader is drawing. We don't have to do, we have to do the pass to generate this buffer, but we don't have to do a screen space apply of the shadows or anything like that. We can sample it all right in the object shader and get really nice shadows and ambient occlusion all for cheap. So another thing that was part of the look that we really wanted to do is we wanted to have a game that sort of riffed off the comic book style, but we didn't just want to slap the traditional outline on everything and be like, yeah, it looks comic-y. What we really wanted to do was make it look almost like an unfinished drawing where somebody had really spent time on the things that are in focus, and the things that are off in the background, they just used a wide pen and sort of roughly sketched it, right? And so for that sort of unfinished drawing, we use the lighting to determine where that happens. And you basically get the sketch effect in your shadows here, right? So that it looks like somebody sort of didn't finish those parts. Anywhere where there's heavy shadow, it's very sketchy. Anywhere where it's not, it's very clean. And so to do that, we take the unclamped lighting value. This is the n.L, the normal versus the light. Gives you the dot product gives you a -1 to 1 for your lighting. So you take that, and we basically just map that to, at -1, it's going to be black, and at 1, it's going to be white. And then in between, we sample a texture, and we have these 3 sketch textures. And these have to be specially processed with maps and stuff to make it all stable, because we want it all to be temporarily stable. We don't want to move around and have everything shimmer, right? So when you do that, you get these various lighting levels, and that gives you this sketch effect in your shadows. So fog. Fog, we basically, Eric has this great paper on fog, and I'm not going to bother to explain the details because you can look at it there. We basically modified this technique to work with our stuff. We can do it all in the vertices and get this nice depth-aware fog that looks really, really nice as it comes up. And we can even just cover the whole ground area of the buildings and have just the tops of the buildings poking out of the fog, which looks amazing. So to get this all to work at frame rate, we need to use multi-resolution rendering because some of this stuff is rather expensive, and we render with our post-proc effects and things like this on all the time. So what we actually do is we render, we have a device resolution which we're rendering at, which is based on the DPI of the device, and we render the world at a sub-resolution of that. And we look at the device, what type of device is, what's its DPI, what's its physical size, things like that, to figure out what resolution we should set this stuff at, what's its performance capability. And so on a low-end device, your actual buffer might be like this proportion. On a higher-end device, it might be quite a bit larger. Now, we use a 16-bit buffer for the world rendering, which would normally cause a lot of banding. And on our highest end, we actually use lower res with MSAA turned on because it looks a little bit better than using the full res. And that's mostly because when we do the upsample, we apply all the post-processing. So when we go from that 16-bit buffer that's low res and we upsample to the high res buffer, we can apply our blur, vignette, color correction, all of these things. And any banding that was introduced is basically just blown away from that. So you can't really tell the difference. If you switch the buffer to 32-bit, it doesn't look any different, really, because we have all this post effect going on. And then we render the UI on top of all of that. So asset bundles. If anybody saw my Unite talk from 2 years ago, I went really deep into our asset bundle system and how we dealt with that for 30,000 asset bundles on a project. It was a nightmare. And we have improved that quite a bit. We have kind of a new workflow. We worked it out with some people from Unity, helped us, which was great. And so the strategy is we only mark the data that we want to load like from code. Okay, so if we have a prefab that we're going to load from code, we put that into a bundle. We don't put any of the other stuff in the bundle. Okay, and normally you'd have to do that to prevent it duplicating textures and all these things. At build time, we parse the dependency list. So we basically look at all the things this is dependent on of all the asset bundles across our entire game. And if we have a large asset, a texture or sound, we just put that into its own bundle because it's large enough that it probably should be. And textures and sounds are usually shared, so that's a pretty good thing to do anyway. If an asset is referenced by 2 different bundles, then what will happen is Unity will make a copy of it for each bundle if it isn't in its own bundle. And we don't want to do that. We don't want to have duplicated memory, right? So what we do is break it out into its own bundle and assign that automatically as part of the build process. And then if you have a unique asset that's small, we just let that get sucked up into the bundle that references it because it might as well be part of it. And we just name these things by path. So we take the file path and turn that into an asset bundle name. We don't use variants at all. We used variants in our previous game, and it created a lot of problems for us. Instead, what we do is we build the game once for the high end and once for the low end. Right? We just build the entire manifest, all the asset bundles, et cetera, a whole new copy of it. And that works out to be a lot easier. So what we do to get the variation, variants are often used for things like lower res textures and swapping out meshes and things like that. But what we actually have is we have a preprocessor that before we build a low res bundle, it checks out all the data, finds all the textures that were going in our build, it checks them all out, and it basically modifies their settings to lower them all, which will then download them from the cache server if they've been cached, and if the cache server works. And then it will build that version of the assets, and then it'll revert it all. And we have some overrides, so artists can say, hey, don't lower the res of this texture, or lower this one more, or whatever. And so this pipeline is a little tricky. You have to deal with the fact that now you've changed the settings, which means the asset importers you have will re-import, and they'll try to set the settings themselves, and so you have to short circuit all that. And we had to write our own P4 integration to do it because it kept, the ones that we tried for Unity kept checking out things they shouldn't and stuff like that. And this was actually really useful because in 5.2, when we were working on our last game, we had lots of issues with the cache server not working. And we actually managed to find lots of bugs to file with Unity on the cache server because our build system literally required it to work 100% of the time. Otherwise, our builds would take 18 hours. So we're able to help them find a bunch of bugs in their hash generation that were causing problems there. So we want loading to happen as fast as possible on a mobile game. The mobile audience is very, very fickle, and any amount of time you waste of theirs is a chance they're just going to flip to something else. So we have nothing in our apps. It's basically just a loading screen and an error dialog, a couple things like that. And we also do this for WebGL. On WebGL won't even show you like a loading screen until it's fully loaded all the data that your app includes. So you really want to cram it down as small as possible. So that's all we really have in the app. But that makes loading time a lot longer when you start up the game the first time because you've got to download all of that. But everything by default is basically load on demand, right? So to optimize this, because we have this theory that users are more tolerant of downloading something from the asset store, or the app store for having it take a little more time than they are for once they start the game on their device and see your loading screen. We actually don't have metrics to prove this. We have metrics to know that loading is a big deal for us, but we can't really time the time in Apple's or Google's system. So But we have this theory that is cheaper or more acceptable to the user. So what we actually do is on iOS and Android, we look at what we have to load, and we bring some of those asset bundles and we include them in the app so that that data is there ready to go. We do this on every build. And so if the data that is on the server has a different hash, then we'll pull it from the server, so because we've updated it or changed it. But if the data is actually the same as what's on the server, we can just grab it from the streaming assets folder, and that increases our initial load time for first-time users. And then everything that we don't need to load right away is deferred, so like background music, things like that. We're just loading exactly what we need at any given time to make this as fast as possible. So this game for each detail level has about 6,200 asset bundles, so it's about, 12,000 asset bundles in total, which is significantly less than our last game, which has been great. The whole game in HD is about 470 megs, and at any given time we have about 400 asset bundles loaded or so. And when you're scrolling the map around, you're constantly loading and unloading asset bundles, so we're really stressing that system, loading them as fast as possible. So asset bundles are still like my most hated feature in Unity. They've gotten a lot better in terms of being able to trust that they work and stuff, but they require an incredible amount of coding around everything. And we had to merge a bunch of fixes back from newer Unities and things like that to get it all to work. They still have some known issues that are surprisingly, they're being fixed, but surprisingly late in the game. Up until 2017, on Android, every asset bundle you load, regardless of how big it is, takes a half a meg of buffer data, which if you load 400 bundles like we do is 200 megs of memory and the total amount of bundle data that is for us is well under 200 megs. So that has now been fixed, but we constantly find new things, little race condition issues and issues with www in this system. So I want to give some credit to the artists who worked on this. They worked under really tight constraints, like having to build everything as these tiny little models and then build it all up in these little pieces is really tricky. And we hire very technical artists, which I love because these guys just, we tell them the constraints and they stay within it, which is wonderful for me. And then since Greg couldn't be here, I just wanted to point out the things that he worked on. He did a lot of amazing work on this as well, so I don't want to take all the credit. So yeah, that's the bulk of my talk. I have some bonus slides as it looks like we have a few minutes, or I can take questions. That's up to people. Bonus slides? All right, just a couple little systems. I'll go over them quick. For outlines, we did want to outline the guys moving around because it sort of highlights them. You can't just like slam another shader pass on there because we need everything to batch. So what we actually do is we use a replacement shader to redraw all of those objects, and we use an old trick, which is to basically just flip the polygon facing and move them out a little bit. And so we can actually do that pretty easy with replacement shaders. And that allows us to get the outlines all in a single pass, and it all batches, which is nice. The day-night cycle, so we have a full day-night cycle, which has like keys for lighting and color correction and things like that it can do. We actually synchronize it between clients, basically by looking at your date and generating all the day data from the nearest sort of checkpoint date that it figures out. And so if you're on two different clients, you'll all have the same weather and day-night cycle and stuff, which is just kind of neat. And then for weather patterns, like I normally would use noise functions for this kind of stuff, but I found them kind of hard to control for what I wanted out of weather. Really what I wanted out of weather was sort of like, hey, don't have two storms. Like if you have a storm, don't have another one for at least this long and things like that. So I parameterized it all that way, and then basically when it loads up the game, it just generates weather for, I think it's, 481 days of game time in the future. And then when it runs out, it generates them again. And this is all synchronized from that key point, so it's all synchronized with everybody else's client. But basically, it ends up becoming just 1 byte, and there's 256 possible weather states it can be in. And so it just generates the weather states and stores a byte for each one. So it's super efficient that way. And with that, we adjust like particle effects and post-proc and things like that. So yeah, those are just some little things I left in there. I'll go back to questions. If anybody has questions on all of this. All right. Nobody got any questions? Then we're done. Thank you.